gentlemen, good evening and welcome to the Royal Academy of Engineering. My name is Robert Mayer. I'm Professor of Engineering at Cambridge, and it's my pleasure as Senior Vice President of the Academy to chair this evening's lecture. Before we start, can I make the usual plea to ask you to switch off your mobile phones? And I should also point out there are 2 emergency exits. This lecture this evening is the second in the Prime Innovator Lecture Series. And we're very fortunate to have Dr. Mike Lynch as our lecturer. Mike is a fellow of the Royal Academy of Engineering. He studied engineering at Cambridge and obtained his PhD there in mathematical computing. He's a highly successful technology entrepreneur, having founded a number of companies, notably, of course, Autonomy, the UK's largest software company. Mike was recently named by the CBI as Entrepreneur of the Year, and he's especially well known for his pioneering approaches to search and information processing technology. So it gives me very great pleasure to invite Mike to deliver his lecture on commercializing meaning-based computing. Mike.
Well, first of all, thank you all for coming on such a rainy evening. I must say you are probably the most daunting audience that I will face this year. And for those of you that are experts in any of the things I'm going to talk about, I will apologise in advance for the gross generalisations and simplifications that will be there. But what I'm hoping today is that I can get across a spirit of some of the rather radical things that are going on in terms of how computers interact with information. So my background was originally doing research at Cambridge in the areas of pattern recognition, and luckily I had no business training and therefore didn't know what all the problems would be, and so decided to set up a business, and that grew into Autonomy. Now, for those of you that aren't familiar, here's a little bit of financial background. Autonomy is about a $6 billion market cap business now. We do most of our R&D in the UK, and we spend about $130 million on R&D each year. It's the biggest department in the company, and it's really about tackling all of these interesting problems. So let's talk about the interesting problems. Well, to understand what we're going to talk about today, you really have to go back to the late 60s. And in the late 60s, this is when people first realised that computers could perhaps be useful in a business environment. And the problem was that if you wanted to use a computer to work with business, there was no way that the computer technology could understand the information that was actually used to do business. So people would have a conversation, they might write letters to each other, and of course this human interaction has developed, and now we may send videos to each other or voicemails or whatever. But the point is that that's all information that's in an unstructured or human-friendly form. Computers had no hope of handling that. And so what people did was they looked for repetitive processes where they could define the process and the rules around it, and then the computer could actually handle that and add value. So, for example, the computer had no ability to understand a conversation that 2 business people might have. But what it could do is you could solve the problem of what something meant by where you put it. So we're familiar with this today. If you have an Excel spreadsheet and you put a particular number in a particular row and column, that number derives its meaning from its position. So that's what gives away what it means to the computer. And then it can apply rules. So for example, we could have information laid out in a very structured, formal way, and perhaps in the third column we'd have a list of numbers, and those numbers would actually represent inventory in a warehouse. So the computer could watch those numbers, and perhaps if one of those numbers got near 0, it would then know that it needed to issue a purchase order to get more teddy bears into the warehouse. And of course what you had done there is automated a task that would have been done by a human being. So sadly, in the late 60s, some poor purchase ledger clerk lost their job and the computer replaced them, and you had automation. And that's basically what has driven the IT industry in the last 40 years, is that automation of those well-defined, highly repetitive tasks. What we need to do, though, is actually say, well, why can't the computer move forward and start to handle all of the information that is still in a human-friendly form? And by that, I mean information where the computer traditionally couldn't interpret it. So, for example, a computer can send an email between two of us. It can store that email. It can route it. But generally speaking, it can't understand what the email actually means. And therefore, whenever anything has to happen to that email, a human being has to read it. And so there are large numbers of people involved in jobs all over the world where what they do each day is read emails and do something. So an example of that might be a compliance officer in a bank. If one of these hedge fund trader chappies suddenly wants to do something illegal, the compliance officer should read that in the email and stop it being sent and stop it. And this is a generic point. So people are employed in all sorts of different roles just to do these kind of tasks. So, for example, the call centre agent that you ring up to find out how to program your phone, or indeed the intelligence analyst that's listening to a phone call that's coming in, or someone monitoring a security camera, looking for someone who's breaking into a building. These are all tasks where people are processing information that is in an unstructured form, one that's more directly consumable by human beings, and making a decision. So the vision here is, can we make a computer actually understand at some level, and we've already hit our first philosophical problem there by using the word understand, meaning, and that's our second philosophical problem, and take an action resulting from that. And this is the area which is becoming known as meaning-based computing, so the idea that a computer can make a decision by virtue of what something means. So it can listen to a phone call, read an email, perhaps watch a television show, understand the meaning, and then make a decision. Now, the interesting thing about meaning is, how does that differ from what goes on at the moment? Well, if you are used to using a search engine like Google or something like that, and you wanted to find articles, I don't know, how to treat your dog for fleas or something, you would probably walk up to Google and you might type in as your first word, dog. The important thing to understand about that type of technology is it has no understanding of what that character string means. The basic process for a search engine, keyword search engine, is to take those three characters, D-O-G, and look for where they occur in documents. And then it will put those documents on a screen, and there are all sorts of attempts that are used to work out which document should come first. So perhaps if the DOG appears in the title, you put it higher in the list. In the case of the internet, popularity is usually a good thing. So if you type Madonna, and the computer's got to choose between the singer's homepage and the Madonna Laundry in Chicago, the way it separates out that is it picks the most popular page and puts that top. And almost by definition, the most popular page is the one that's going to keep most of the people happy most of the time. But the reality is, for many of the things that we might want to do, popularity is not a good measure. But more importantly, because there's no ability to understand meaning, and we're just looking for keywords, the ability to get to the level where the computer can actually take a paragraph and make a decision is much harder, because an individual word doesn't really give you the ability to understand meaning. So this is the area of meaning-based computing. It's a loose federation, and it includes things like speech recognition, what's called gist recognition, which is speech recognition when combined with conceptual understanding. A lot of work in vision, where a computer's trying to extract meaning from a scene. And of course a lot of work in handling textual information, where a computer's trying to read an email and understand what's going on. One could argue that there may be other aspects where you can extract meanings. For example, a camera looking at how a crowd move might be able to extract some level of meaning from that. Now, this is a very difficult problem. So how do we go about thinking of solving this problem? Well, this is just a very simple example of, as soon as we move away from typing DOG into a computer and we actually want to look for dogs, Well, the first thing is dogs come in many sizes and shapes. So we've got all the usual things you'd think of: big dogs, little dogs, angry dogs, passive dogs, smelly dogs, furry dogs. But then we also get into a problem with meaning that the thing on the left is generally considered to be a dog. Therefore, it has the meaning dog. And there's going to be many contexts where that's perfectly acceptable meaning for it. So how do we define that that's a dog? The thing on the right, most of you will consider is probably a dog. Now, let's just sort of step back and become a computer programmer for a moment. How do we write a set of rules that's going to work out that that's a dog by using normal programming? So basically if then else. Well, the first thing you do is when you sort of show this to a student is they say, well, if it has ears and a nose and it's sitting, then it might be a dog. And of course what you have to do then is say, right, well, okay, that's great, but how do you know if it has ears? And then you get down to the next level, which is, well, if there's something towards the top of it and it's sticking out on each side and there's one on the other side, and you can see where this is going, you start to get into this incredibly complex, nested idea. And the problem is that people who like to think that the world is ordered and you can write a rule for everything will continue down that rat hole. And what they forget is each of those rules has a probability associated with it. So actually, there are one-eared dogs in the world. Now, they're unlikely, but they exist. And the problem is, if you're going to nest each of those rules and each of them's carrying a probability, you have to start chaining those probabilities. And what turns out is that very soon, your ability to discriminate on those kind of rules in these kind of situations becomes very, very hard, because as human beings, we're very good at writing a rule with a small number of quite deterministic variables in our conscious thought. But when it comes to a large number of subtly related variables, we're very bad at that. So this is just a very simple example of meaning. And of course, the problem with meaning is it transcends a whole series of formats. So here we are looking at the idea of a dog in a cartoon and in an image. We could still have exactly the same meaning in a paragraph talking about man's best friend. We could have the same meaning in a paragraph in French talking about man's best friend. We could have the same meaning in a phone call that's recorded from a teenager using terminology that none of us would recognize about a dog. What we have to do is map all of that back to the same idea of meaning. The other thing that this slide shows that's very important, and this is in some areas considered quite heretical, is that meaning only arrives through experience. And that's a slight problem, because you're starting to lose, or at least you think you're starting to lose, a concept of objectivity, which as scientists we've all been raised with the idea that things should be objective. If we look at the image on the left, it's hard to argue that it actually bears any relation to a dog at all. For a start, it's leaning against a wall with a t-shirt on and it's up on its hind legs and it's wearing sunglasses. All of those things should rule it out as being a dog. But we'd all agree it's a dog. And the reason we all agree it's a dog is because of our experience in life. So if someone who came from a culture where they had never seen Snoopy and never interacted with other people who'd seen Snoopy, saw that image, it would be very unlikely that they would consider it's a dog. Very nice example of that is mice in cartoons. When you actually think about what a mouse in a cartoon looks like, it bears almost no relationship to the actual creature. So, let's take a much simpler problem and let's just deal with a little bit of text. So, what we might want to do here is spot news articles for, I don't know, Reuters or Bloomberg or something, that are about violent events in Israel. So things that are going wrong in the Middle East. And a very simple place that many of us would start, especially those of us with a computing background, would be to try and think of keywords and construct some sort of Boolean query. So we'd look for the word Israel and Palestine, or Palestine or Israel or something. And initially we might think that's going to find all the news articles. The problem is, obviously, because it's not understanding meaning, it's going to hit things that are not relevant. So that is not relevant to the fact that we're looking for breaking news stories on bad news coming out of the Middle East. So what we then naturally do is we start to try and add more information. Now here we have a problem which is called referential meaning. So the words Palestine and Israel, which were in our original idea of what we were looking for, don't appear in this because it's written in a format where we are supposed to have supplemental knowledge that Mr. Arafat has got something to do with Palestine. And this is a real problem when you deal with human beings because that's a knowledge-based reference. What you get is cultural-based references. So a very simple example of this might be, he's as good as Wayne Rooney. Well, we might know what that means if we know who Wayne Rooney is, but that's not something which is inherent in the statement. And of course we can carry on, and we can try now. So for example, we could add in the word Arafat, and we can put in suicide attacks and state of emergency, and we can keep going on and on and on with this. And the problem is that this just gets really very complicated. And of course, every time something new happens, we have to go and edit the expression for what's going on. And now we have a very good example here where we've got really quite a complicated little structure there now, and we're still going to miss that article. So we carry on. And you can imagine we can carry on indefinitely. And to give you an idea, if you're trying to spot articles on Apple Computer flawlessly using this kind of method, the expression is 20 pages long. And it has to be continually edited every day. Every time Apple bring out a new product, all of that has to be edited. And of course, this breaks down. It breaks down for the probabilistic reason. If we write, she's a star, and we think somewhere else that star is a cosmic gas ball, we have to be very careful that the computer doesn't conclude that she's a cosmic gas ball, because it's not understanding a contextual relationship. And then we get to the ones where there's a probability. So if we see the word leader, it might be that this article is about the President of the United States, but it might be that the article is about many other things. So the relationship of that idea to the word leader is quite weak. Whereas if we see the word president, the relationship of that to the article perhaps being about that is much stronger. So the point I'm making here is that these links are not hard and fast. Not only do they change as a version of context, but they change in meaning. So, how do we solve these kind of problems? Well, the first method up there is these sort of very structured approaches, things like Boolean querying and, for those of you familiar, things like markup languages, which are basically more complicated versions of that kind of approach. And you'll hear and read a lot about people who would love to organise the world into pigeonholes under that. And there are various reasons we can spend time on, perhaps in the Q&A, why that doesn't work. And actually you can show using probability why it doesn't work. The two big approaches to try and understand these problems with text are linguistic, or computational linguistics, where you understand the idea that language has a structure. So it has nouns and subjects and verbs, and the idea is you write a big computer program and it goes through and it parses all the bits of speech, and then by doing that parsing it can understand language. And lots of research goes on in those areas. It has, and this is a slightly controversial statement, not been wonderfully successful, and the reason is really summed up by this simple sentence here. The dog walked into the room, it was furry. What was furry? Well, actually, if you look at the rules of language, it biases slightly you towards the fact that the room was furry. Now, in Manhattan in the early 70s, there probably was some chance that the room was furry, but generally speaking, most people would go for the dog being furry. And why? Well, again, it's experience. We have knowledge of dogs and we know that they're furry, and therefore, when we are unpacking the language, we're using that knowledge. The necessary information to unpack the language is not held in the language. And so what you then end up is trying to create a property of dogs have this property furriness, and they have action of going on walks and all this kind of stuff. And the problem with that is that it leads to an incredible need to maintain all of that understanding and continually maintain it, very like the topics that we were just looking at with the Boolean querying. Where this does work very well is where you have the same questions asked over and over again. So, for example, in a help desk, because what an understanding of language can do is take the 120 ways in which you ask the same question and normalize it to one form. The method that's turned out to be most powerful is to treat the problem as a probability problem. Now, this is very counterintuitive because we all went to school and you did English language in one class and you did maths in another class, and never the two should meet. Well, actually it turns out that maths is very helpful in handling language. So let's take this sentence for those of you that of a similar age to myself. Gazza and Shazza in Razza. It's a Sun special, this one, a headline. And now the interesting thing about Gazza and Shazza in Razza is most of the UK population would know what that was about. Of course, it's our wonderful Paul Gascoigne and his wife Sharon, and apparently they had a dispute. And that's what the Sun is referring to. Now, we've got a few linguistic problems in that sentence. But the problem is we all understand what it is, and we don't have to have a key at the back of the Sun where we look up Gazza equals Gascoigne. The context is enough for us to make the link. And the way this works is, imagine that you had all those wonderful monkeys that mathematicians love. And we had all the monkeys, and we chopped up the British Library, which would save a lot of money, and we took all the words and we put them in a big bag. And the monkeys just pull out the words and they stick them on a page. Well, occasionally after a few tens of thousands of years, they might write something useful, but generally it would be rubbish. It would be gobbledygook, it would be a random stochastic process. Actually, when we look at something that someone's written, it's not random. So if we see the word dog, the probability of seeing the word walk is actually higher than it should be by random chance. Why is that? Well, the reason it is that whoever wrote the sentence had the idea of the dog in their mind at the time they wrote the sentence, and one of the things that dogs do is they get taken on walks. So although it's not a certainty, you see this probabilistic anomaly. And then you can use some very interesting mathematics to back-invert that observation and infer the existence of the idea of this thing called a dog, and that it goes on walks. And what you've got is a system that can learn from real language, so it learns slang. It doesn't mind if the grammar is correct, which, of course, by the way, if you look at text inside a corporate, with the exception of letters to the boss, nearly everything is grammatically incorrect. So most of the time it isn't. What's the difference between these two? Well, the quickest way of understanding it is linguistic is a bit like learning French by being 16 and stuck in a room in Stoke-on-Trent. The second one is learning French by being 2.5 and living in Paris. And that's the difference you get. You don't know why you understand French with the second one, but you do, and it's very robust. The first one, you could understand all of the grammar and explain all the different tenses of French and all that sort of thing. So, very quick introduction to it. Now, who do we have to thank for all of this? Well, this is the Reverend Thomas Bayes, and the problem with the Reverend Thomas Bayes is those people that have become what are called in the trade Bayesians are sort of a bit like a sort of Saul on the road to Damascus moment. They suddenly become completely obsessed, and they can't make a cup of tea without seeing it in a Bayesian framework, and which of course it is, but you know. And the interesting thing about this chap is I suspect in 100 years' time people will realise that what he said was incredibly profound for the next 50 years of our development. And he was an English country vicar, and he tried to produce a mathematical approach to proving the existence of God. He was in search of the divine, which he didn't manage to do, to our knowledge. And he didn't publish his work. He was quite a modest man, but luckily for us, he had a self-publicising friend, which is very important, and that was Mr. Richard Price. And he published his work after his death, and that's how we have Bayes' work. Now, some of you will come across this in sort of basic Bayesian statistics, but the area that's very powerful is what's called Bayesian inference. And one can have long philosophical discussions about this, But the thing that's very important when we come to look at meaning is it's the bridge between the objective world of mathematics and science and the subjective world of meaning, because it allows to build in experience into how things are understood as meaning. And that's a very fundamental bridge, and why I suspect he will be remembered for many, many hundreds of years to come. The other person that's very important is much more recent. This is Claude Shannon. He worked at Bell Labs. He as you can see, only died fairly recently. And again, massive generalization. Many of you will have come across his work in how you squeeze information down to send it over communications channels. But as part of that, he basically came up with a way of working out how valuable information was. And this is all to do with probability. And if I say to you, come to the window, outside there are, and you've received that message, there's probabilities of what comes next. And if I say, come to the window, outside there are cars, probably no one moves. Whereas if I say, come to the window, outside there are rioters, you probably go and have a look. And the important point there is that the probability of hearing the word cars in that context is quite high, and it's boring. You're not telling me anything because I know. Whereas if you get something which is unexpected, the informational value of that is much higher because I didn't know it in advance. So what we have here is a fascinating tool to actually start to understand which bits of information are more valuable. And because it's based on probability, we can build in context. So what's valuable to me may be different to you. So now we've got to make a big step. If I asked you to go and find me articles from Google on penguin, most of you would go and type the word penguin into the search engine. And the reason you do that is that in your rational conscious thought, you've been trained to look for strong, reliable things, rules, pieces of information. And the strongest piece of information you could probably come up with to find the word penguin is to type in the word penguin, because you'd be looking for the idea penguin. However, depending on the corpus, it's not perfect. So, for example, the first document we hit might be about Batman and Robin and their arch nemesis, the penguin. And then we may have another go, and we may hit publishing penguins, the publishing house. And then the third time, we might hit an article which is actually about the flightless bird. The important point, it depends on your corpus, but the accuracy of just typing the word penguin and your first article being about the flightless bird depends on the corpus, but 87% or so. Now, that's an example of a small amount of strong information. Look at this sentence. None of these words on its own is useful. If I gave you the word black and I said, what's this article about? You wouldn't be able to tell me. However, turns out that the probability of those words all occurring in an article which is not about penguins is about 3%. So the point I'm making is a large amount of uncertain information is much more powerful than a small amount of more certain information. And that is counterintuitive to how we often think about problems in computing. And of course, then we have our lovely penguin. So, let's use these two and see where we can go from here. So at the top we have Bayes' theorem, which allows us to manipulate all of these probabilities. And at the bottom we have Shannon's theorem, which allows us to work out which things are more interesting. And by putting them together, we can start to do things. Now, remember I was telling you that probability is a bit of a difficult thing. Very simple example which people that work in this area know very well, so I'm banking on the fact that most of you don't. The good news is that tonight you have the chance to win a Ferrari, perhaps. If you believe that, you'll believe anything. Behind one of these doors is a brand new Ferrari, and behind the other two doors there are just goats. Okay? So, what we need you to do is pick a door, as they say in the trade, any door, and work on that. So let's do the experiment. And you've all got your doors picked, and I open a door. Right, so who's out? Anyone going to admit to picking the blue door? Yes, you're gone. Okay. Now, for those of you that are still here, so you either picked the pink door or the yellow door, I'm going to give you a chance to change your mind. Who would like to change their mind? Okay. Who would not like to change their mind and would like to stick with their door? Right. Ah, right, Alex. Why are you not changing your mind? Absolutely. Anyone else? Why they're not changing their mind?
I think because you I've chosen pink because I think you expect a male it's not choosing.
Okay. All right. Well, there's all sorts of interesting areas, but the fundamental point here is that if we do this experiment with a group of Nobel Prize winners, the Nobel Prize winners all insist that there is no basis, all is not true, most of them insist that there is no basis to change your choice. Okay, so if you picked yellow, why change? If you picked pink, why change? And the simple argument is, well, we've opened the door there, the goat's gone on that one, so now we've got two doors, therefore it's 50-50, therefore there's no rational basis to change your mind. Well, the fascinating thing about this experiment is that's wrong. And it's quite hard to grasp, and I do not want emails from you from the next 6 weeks telling me why this is wrong. I'm going to give you the explanation in a way which I think is that there's many different ways of trying to explain this, but the quickest way, I think, is imagine that we had 1 million doors, okay? We had 1 million doors, one Ferrari and 1 million minus one goats, okay? And I take those, you pick a door, and I open all but two of the doors. So now what you're seeing is 9,098 goats and two closed doors. Should you change? Well, of course you should. And the simple reason is you only had a 1 in a million chance of picking a door in the first place. Therefore, the Ferrari is almost certainly in the other door you can't see. Okay? Now, if that hasn't worked for you, I suggest you get 3 coins, 3 cups, and sit at home for an hour and just repeat it lots of times. The fascinating thing about that is so counterintuitive to the way we think, because what we do is at each stage, we cut off the information that we're carrying forward. And actually, what's happened is, when that door was opened, I gave you a lot of information that you have discarded, and that's why we have that probability difference. Now, there's been some very interesting experiments, and as I say, Nobel Prize winners not only get this wrong, but incredibly vocal for the next 2 hours about why it's wrong, until you either make them go away and do it with pennies and cups, or you give them the 1,000-door thing. Do you know what gets it right? Your common or garden pigeon. If you do this experiment a few times with the pigeons, they very quickly work out to change the door. And that's fascinating, because the Nobel Prize winners are thinking at a rational level. The pigeons, presumably, and I'm not going to get into any disputes with pigeon experts here, but are not running mathematical consciousness. They learn how to weigh probabilities in this kind of Bayesian manner in the real world, because they have to in order to survive. We probably have that innate skill, but at a lower level than the rational way in which we think about things. So how do we use that? So we have a nice document on the Labrador Retriever. We go through, we find all of the interesting probability words, and then we back calculate from those words into an idea. And that means we create the idea of a Labrador. And because we can now chain probabilities, we can understand how near, and this is the idea of nearness, is a Labrador to a puppy. Well, puppy and a Labrador, quite near. A Labrador and a boiler valve, not near, generally speaking. And we're doing that because we can chain through probabilities for all of these things. What that means is that if we are, for example, investigating a serial murder, and we have lots of different statements from up and down the countries over many years, we can automatically understand that if we're starting to see in the statements of witnesses that there was a teenager with a puppy and someone else saw some guy with a Labrador, and a bloke with a dog, and a French student who was visiting an homme avec un chien, that those are actually something's going on and there's a guy using a dog to cover themselves while they're stalking their victims. That is the ability to move out of the domain of the expression, the words, into the domain for meaning. And that's a system which is actually now in use for those kind of things. I wanted to also give you another important point, which is when you're doing these things, you use every trick you can. So if we want to understand what a TV program is about to make that searchable, we can't do things like manually tag it. So what we do is we take all of the information sources. So we take speech recognition, and we use the fact that we get a running idea of what the ideas are to improve the speech recognition. So because we know that dogs go for walks, we can build that in to how the speech recognition is done. And then we take things like all of the video information, and all of this has to be put together, not discretely, but carrying the probabilities, so that what we get is an overall view. And so, for example, now, things like television programs become searchable. So this is an example of the power of all of these bits of information coming together. It's what some people call data fusion, and it's very hard to do unless you have this ability to take meaning and probability together. Now, what about turning all of this into the commercial world? So who's actually using these kind of technologies today? Well, the fascinating thing is that the software industry is actually now working on products that are based on meaning-based computing. So the largest software companies, people like HP, Oracle, Adobe, all of the next generation of their products will actually have the ability to handle unstructured information in this kind of way. And what we're seeing in large corporates is it being used to deal with the sort of onslaught of all of the information. We could talk about many different application areas. Perhaps some of the most interesting ones are in online shopping. It turns out because the computer can understand things like blog posts, what people write, it can optimize the transitions through a website. And a new model is actually that the computer, for each individual incoming person, does experiments. It changes the website. Should this arrow be green? Should it come from the right? Should we put, we respect your privacy? And in doing all of those changes, it optimizes the website. And the reason that this is interesting is that of exactly the same inventory and exactly the same products, you get significant uplifts in sales, somewhere between 8 and 12%. So, for example, Delta Airlines, $30 million more in revenue just by allowing the computer to design the website in real time. And the kind of systems that you're seeing now are these. The computer, because it can understand social media, it can understand how products are being perceived, it can see the effect of a TV ad and how that's commented on, extract the meaning from those feeds and use that to run optimizations. It can listen to the call center conversations, work out where customers aren't getting it, change the scripts that the reps use, change the website. And as well as extracting meaning, it can extract sentiment. This customer is talking about this product and they really like it. This person is talking about that and they're very unhappy. And then that is run through optimization algorithms to do things like optimize the pricing, the ads that are shown, take into account the inventory. So the fascinating thing is, this is modern marketing, and it looks like a diagram from an engineering textbook. And the reason that this is taking over is the results are very, very powerful. Because it's very hard, as someone who, for example, is an expert in branding, to get a 15% uplift off of exactly the same business. Whereas when you allow the computer to treat it as an engineering control problem with optimization and feedback, you get very powerful results. This is another area that's being revolutionized. The basic principles of the legal system date back to the Romans. You have a dispute, the two sides bring the facts, they place them in front of the judge, that's called discovery, and the judge is supposed to work out how the law applies and come to a judgment. Well, we've entered electronic age, there's vast amounts of information. So either you throw away a basic principle on which civilization is built, because you can no longer go through the information. So you say, well, turn up in court with the emails, but obviously we can't do the instant messages. Well, immediately, if I'm going to commit a crime, I'll use instant messaging. So what you've got is a situation now where there is just too much information for a human being to go through. And remember, it has to be gone through on the basis of meaning. You know, we want to know what this company knew about the effect of cycloalkanes on the developing child. That's a meaning. It's not a keyword. And so the technologies are having to move fast in order to allow the legal system to carry on. You look at regulation, all of the issue about regulating the banks, that is having to be done with computers looking for the information. In fact, the French trader was caught by these kind of systems. Actually, it read its emails and discovered that he was making up emails that didn't have the same meaning as what was going on, and flagged that up, and he was caught. One of the big areas where you don't have any choice is social media. It's real time, it's happening so fast, human beings can't analyse it, there's so much of it, there's a lot of value in it, and one of the wonderful things about it is it uses a different language. If your 17-year-old writes wicked, it may well be they don't mean bad, they mean good. And that is just the tip of the iceberg. You have whole subcultures of language use. So if you have a computer that's been told that wicked equals bad, that's not going to work, because actually wicked means good. So it's also another area in intelligence where words are used out of context. If someone says, I'm going to meet you at the station and I will give you the cake, in that environment it's quite likely that the word cake doesn't mean a baked good. It might mean something else. And the computer mustn't be thrown off by the fact that there's a word being used out of context in that situation. In Wall Street, because of the data flows and all the regulation, it's becoming more and more important for the computer to be able to do things like work out which information has to be archived. There are now rules, for example, about which citizens' information you can store in which country. So you imagine you're a bank, you've got email traffic. How do you work out what's talking about a Swiss citizen, which therefore is not allowed to be stored on US soil? And there are hundreds of these kind of problems now, which are having to be addressed by a meaning-based approach. And then we have the information that's all around security and protecting the country. Information flow is becoming easier, more of it, and the amount of organisation and resources to do a certain fixed amount of damage is becoming less and less. So more sophisticated methods of filtering where the resources need to be applied are becoming a very key area. What you don't want to do is replace the person, but what you want to do is get the person looking at the things or dealing with the things that are actually really useful. One very interesting area is in medicine. Obviously, if we start to use Bayes in, for example, problems of diagnosis, that's a probabilistic area, but we have a lot of prior information. So, for example, if we look at the medical records in a particular hospital, we know a lot about what the prevalence of various types of problem is in that hospital, and therefore we can very quickly put up the most likely list for someone to consider and do the tests for, rather than, for example, just because the symptoms happen to match a tropical disease and we're in the north of England, that might be very unlikely. Whereas if we're a hospital in the Southall near Heathrow Airport, that may well be a lot more likely. So using these kind of technologies to bring that information together and fuse it together are very important. So just to finish up, I'd like to tell you a little bit about the history of getting to this situation. When you look at autonomy now, it's sometimes hard to remember that it was started by a couple of people, and that was 14 years ago now. And the difficult thing then was getting finance. I had an academic background, and we didn't know how to get finance. And I was very lucky in that I got introduced to an eccentric in a bar, and this chap had discovered one of the major rock groups, and his life at the time I met him consisted of carousing, drinking long into the night in a Soho wine bar, waking up at about 4 o'clock in the afternoon and then repeating the process as long as his liver would hold out. And luckily I met him at about 6 o'clock, by which time his ability to do deductive reasoning was very limited. And he lent us £2,000, and that got the business going. Then we had the issues of making the business seem larger than it was. There were big issues, a very famous story at Autonomy. We had an office which was just large enough for one desk. We couldn't afford any more. And the first few potential customers that came through saw this office and decided they couldn't possibly deal with a company this size. But we had one secret weapon, which was we had a broom cupboard. And so we put a big sign on the broom cupboard that said, "Authorised personnel only beyond this point." And soon we started winning business. And the important thing about this, of course, is that if you go to a big Autonomy office now and you see a door with the sign "Authorised personnel only beyond this point," you have no idea whether there are 500 engineers or brooms behind it. And we like it that way. So what are the sort of lessons in doing this? Well, for engineers, it's very important to say marketing is very important. I think we as engineers often think that marketing is cheating, because at the end of the day, if you've got the best product and it catches more mice than the other chap's mouse trap, then that should be it. And of course, the reality that the world doesn't beat the path to the door to see the best mousetrap unless you get a lot of marketing to do that. So it's important in taking great technology advances we have in the UK that we can actually market them. Another key one is focus. One of the problems you get as an engineer is that all the professionals, the accountants and the lawyers and everyone are always telling you all the things you should do. And you end up with this long list of things to do. And my best tip for you is take all the long list of things to do and just work out what are the 5 that matter and just do those. And what you'll do is you'll get the things that matter done, and the other things tend to look after themselves. I am one of these people that takes this to the extreme. When my email inbox does get too full, I do just take it all and drop it in trash and then wait to see what comes back. And it's a very effective model because the important stuff usually comes back. So, those are some of the tips. Where is all this going? Well, to finish off, I'd like to show you a little bit about where information is going in practical sense. I'm going to show you 3 things. The first thing is, I personally believe the whole idea of a search engine will disappear, and it will look like a very archaic way of doing things, a bit like starting a car with a starting handle. And why do I think that? Well, because the whole idea of stopping what you're doing, coming up with a query, typing it into a box, getting information, then carrying on what you're doing is flawed as a workflow. Secondly, we expect too much of the search engine. If you walked up to a librarian and you said Madonna, how does the librarian know what you want? Now, they could take a guess that you want Madonna's latest coffee table book, but you might be interested in Italian Renaissance painting. And of course, the way we in humans would do that is we'd give the librarian more information. I'd like a book on Italian Renaissance painting, particularly Madonna and Child. And so this whole idea that we have to break something complex down to a word and put it into a box is flawed. So the first thing I'm going to show you is technology which brings information to what you're doing by reading what's on the screen. It's what's called implicit query, and it's meaning-based. The second thing I'm going to show you is that idea taken out into the real world. So now we have devices in our pockets that are connected with bandwidth. They know where we are, they know which direction we're facing, and they have real-time video feed. And what that means is you can bring the virtual world to the real world, and this is what's called augmented reality. And very, very powerful technology. You'll see demonstrations of this, but the real problem is the back end. It's where all of the information is fused together by meaning. And then the last thing I'm going to show you is how media is going to change with meaning. So the big problem with modern digital media is how do you make money when the stuff's copied? Well, because the computer can now watch a film and understand at some level what's going on, you can build the ability to monetize the content into the content. And when you do that, you want it copied. You want to see the stuff ripped off and distributed, because as long as the monetization goes with it, then you have a viable model for media. I think, I hope you'll agree that it's a very, very exciting time for these kind of technologies. It's baby steps. There are a lot of unsolvable problems at the moment. But the real issue in the next phase of computing isn't about the information and the bandwidth. For example, very soon you're going to be able to record your whole life on an object the size of the iPhone, just because that's how storage is going. But the important difference is, actually, that's not useful. What's useful is when you can look at that device and say, where did I leave my keys? And it understands the information and can actually take you to where you left your keys. So this transition into meaning is what is actually going to make the very large amounts of information that are now capable of being stored and transmitted useful. With that, thank you very much for listening.
I share your enthusiasm for the power of probabilistic methods. As you indicated, it's clear, I think, that the more the computer understands us, the more intimately it knows about us as individuals, our preferences, likes and dislikes and so on, the better able it will be to service our information needs in a timely and effective manner. But of course, some people may be reticent about allowing the computer to know us intimately. I'd be interested in your thoughts about the trade-off between privacy and the power of these methods.
It's actually a very interesting one, that, because there's some very clever work that was done on one of the West Coast universities where psychologists came up with those kind of cunning experiments they do. And the experiment was to determine the value that someone places on their private information. And the result was $2.70. And the fascinating thing about it is, that's a generalization. There are certain groups that that's not true of, but for most people, the biggest issue they actually really have, even though they don't like to admit it, is they assign a value to information, and if you take it off them without giving them something in return, they feel you're stealing. And so the sad fact is, as long as you package it with some kind of benefit, people are actually a lot less sensitive about it than they should be. And the slightly worrying thing is the young people are the least sensitive about it. So whereas we all at our age would be quite careful about our private information, if you look at your 17, 18-year-olds, it's almost horrific what they will reveal online. They also don't have any concept that this stuff is permanent. So, if you write something online, then there are various archiving systems that mean that just does not go away. So it's a very interesting debate. I think it's a transition phase between our generation and the next generation. I do think there are ways of dealing with it from a technical point of view as well, but a lot of it is to do with benefits. So, for example, people have no problem carrying a Tesco club card around, and that gives a phenomenal amount of information about what you're doing. So it'll be a very interesting question to revisit in 20 years' time when this generation that seems to be very free with its information actually is older.
Yes, question at the back there.
Thanks for a fascinating talk, Mike. I'm Dougal Goodman from the Foundation for Science and Technology. Two points strike me immediately. One is I have a relative who has early onset Alzheimer's disease. So having the capability of picking up your phone and saying, this is mum, or this is my daughter, is an important aspect of the technology and the way the technology is headed. The second point is I'm very interested in how you analyse emotion. You haven't mentioned music at all. It's always struck me that there's some very interesting search questions about how people interact with music and how composers compose music, and whether you can, for example, identify whether a composition by Mozart is really by Mozart. The whole question of how we respond to vision, sound, and so on is a very important aspect of what you've been talking about.
Yes, it's very early days for the idea of emotion. So, for example, in text, people have been trying to crack the problem of sentiment for a long time. It's just about working now. But that's a much easier problem. So actually working out whether someone's happy or not happy about something that they're talking about. I think you can do all sorts of interesting experiments for looking at for example, musical progression. There are two fundamental aspects that one has to think about. One is there anything inherently in the music that sets that? And this is an age-old debate. So, for example, most people in the Western world would agree that a minor scale is somehow sadder than a major scale. Is that inherent or is that learned? And that will keep, whole research departments going for a long time. If it's inherent, then it's very hard for the computer to generate that in knowledge. Obviously, we can tell it that knowledge. So I think, I wouldn't venture to go there. I think we have an unsolved problem. The one thing I think is very interesting, though, about art, which was alluded to in the video, is we are very interested in things that have a slight amount of probabilistic disruption. And we do it both for audio and for visual. So one of the reasons music is repetitive is to set up a probability baseline from which you will then slightly deviate. And that's the interesting bit, and that's often the emotional bit as well. And it's the same with art. A photograph, is not perhaps as artistic as the picture you saw. I think it was Picasso from memory. Now, that at one level is working. There's obviously faces there, but they're wrong. And as human beings, we seem to love spotting probabilistic anomalies in our audio and visual information. We seem to find it exciting and interesting. So at a very low level, there's something going on there about how our brains are calculating probabilities of what we expect. And then if there's a little bit of disruption to that probability, we seem to be pleasantly surprised. If there's a lot, then the probability framework falls apart, and we generally aren't impressed with that. We consider it noise or rubbish or whatever. So, having said that, it's all very, very early days. But it's a very interesting area, this idea of how we like slight disruption.
Yes, question here.
Ralph Benjamin, Bristol University. Can I just explain how I understand what you said? We are all overwhelmed by the many, many orders of magnitude by the number of bits of data available. By converting this into information, we measure the reduction of uncertainty, which reduces it to some extent. If we've got a number of separate items, then their association gives us a further reduction of uncertainty, more information. But that information still may not be relevant. And you therefore use the probabilistic association of this with its wider context, present and historical, to try to measure relevance. But it may be relevant, but nevertheless trivial. Therefore, the final stage, and the most difficult one, is to establish importance from the context of past and present contextual decisions. And this, as I understand it, is really what you are finally getting at.
Yes, I'm not sure I quite understand your question, but there is perhaps a very important point in here. We have the idea that more information is good. So, but actually, it turns out that to achieve things, our ability to have less information that is higher quality. So, for example, if I was to look out of the window down there tomorrow in sunlight, and I came back and I drew what I saw, I will give you a very rudimentary line drawing of some cars and I don't know if there's a tree out there or whatever. And that will be what I remember of that scene. I will not remember the photographic scene. So, for example, if there happens to be a puddle down there, it will probably not be in my drawing, and I will probably not realise I saw it. But I saw it. I was standing at the window. The point is that what my brain is doing is taking this vast amount of information, most of which is usually irrelevant, and boiling it down to what actually matters for me to make a decision. So one of the interesting things is sometimes when you see people that have had brain injuries and they have a phenomenal ability to draw something, so they can take a building and draw it in incredible accuracy, that's not a good thing, because what they're not able to do is package that information into useful forms of all the details that usually matter and leave the things behind that aren't actually useful in doing whatever the tasks are that are there. So in the video we talked about the idea of not playing with a full deck. What the brain is doing is massive data compression. So you're starting with, if you want to think of it this way, real-time HD video and audio. And there's a vast amount of information. Yet, if I went for a walk and I come back and I see my wife And she says, what did you see? I say, well, I saw some brown cows, and they were looking very well, and it was a sunny day, and then there was a rabbit on the path. The amount of information in transferring that is a tiny, tiny fraction. Now, it may be that I have a little bit more information in my head, I might be able to draw the rabbit, but we've still lost the vast, vast majority of information and boiled it down to something which is a representative meaning. And obviously no one knows how that is done, but there's very little doubt that meaning and data space reduction are very closely related, because what you've got to do is transform the original data space into one of meaning, and what you want to do is preserve the dimensions which are useful to you, but not the ones that are not. And so, we see this in human beings, in that there are some people that, because of their job, will remember and notice things that other people wouldn't. So, for example, a good artist probably would be able to look at that window, come and draw it, and would have the puddle in there, whereas I wouldn't.
So I was trying within meaning to distinguish relevance and importance.
Sorry, what was that?
Sorry, could you say that again?
I was trying within meaning still to distinguish relevance and importance.
Well, I think you have to be very careful about relevant and important, because who decides that? So, as a biological system, probably relevant and important tends to be defined by what gets us through our day. I think the one thing that's important when you take this view of the world is that there's no absolute concept of whose view is relevant or whose view is important. There might be things that we can agree on. So, for example, how to build an aeroplane, that it turns out we would generally have a common view on, because we would do a test and it would either fly or not. But, for example, when I used the example up there of the Middle East, that's got another layer of meaning. If we were to be talking to one side in that dispute, they would interpret and would actually write or tag a news article completely different to the other side, even though it's the same information. So which one of them is correct in how important and relevant they've decided that news article is? It's a contextual answer.
Lord Brose.
I'm Alec Brose, a fellow of this academy. Mike, a fascinating lecture. You're always intellectually challenging, and we try to stay with you. But the title of your lecture was Commercialising Meaning-Based Computing. You didn't actually tell us how you built the biggest software company in the country and been the most successful entrepreneur. And I don't want any company secrets, but where was your biggest early break where you could outperform the likes of Google and Microsoft and make a real business for yourself?
Well, the trick, so put this in context, you have a couple of young academics with very little money, but a belief that this area is going to be very important, and obviously a set of methods to address the problem. And in that situation, what you ideally look for is a problem that is very easy, is black and white to prove it works, is high value, and is very easy to test. And one of the first problems we did was matching fingerprints for police forces. And the reason this was a very nice problem was that it was high value, in that if you had a murder, it would often take fingerprint experts 3 weeks to go through the files just for that one print they'd found. The second thing was there was very little debate about whether the machine worked, because the fingerprint people could take a print that they knew was, Feathers McGraw or whoever, slip it into the machine, and then see if the machine picked out the relevant files. So it was very easy to test. And so what you had was the ability where they were happy to say, well, we've never heard of you, we know you're a small company, but, come along on a wet Thursday afternoon and we'll do a test, and if it works, then we can suddenly, rather than searching fingerprints in 3 weeks, we can do it in 5 minutes, and we'll buy one. So you're much better when you're starting from a sort of engineering background to pick those kind of problems where you can show something which is just, very clear cut. One of the mistakes you often see people do when they're starting with a small business is they do a Me Too product. So, there's some very big company that's incredibly successful out there, and they produce products just a little bit better, and they think that that's going to be enough. And the problem is, when you're a small company, even if your product's a little bit better, by the time the market understands that, you've probably lost some of that advantage. So it's very important to pick a winner when you start. And then, the other tricks are, understand that you have to get out there. So, for example, after we sold that first system to the first police force, we lent very heavily on that police force to go and visit their neighbouring police force. And that may seem obvious with hindsight, but again, it's something that people often don't do, because somehow they think once they've done this one, that's it, and then you have to work that process through. I think the other thing that we found was, you have to be prepared to change your mind. So one of the things that I think is a little bit of a problem with sometimes how the funding works, Autonomy's first product was a consumer product, which was for entertainment, where this technology was put into an animated dog that used to go off and literally pick up documents for you on the internet and then bound onto your computer screen and do that and drop them in front of you. And, that was what we were doing as a company. And then suddenly we realized that software on the internet was free and we'd better go and sell to someone who had money, and we decided that companies had money. And we did a U-turn. And, one of the important things to do, I think, in a small business is be prepared to do a U-turn. When you've got, for example, funding from angels, that can sometimes be hard, because you've got to sit down and, you know what we told you last week? We've changed our mind, we've got to go and do this. But it's actually a very important part of reacting to the opportunities that come up and grasping those things when they happen.
Are there any more questions?
Nat Billington from Hearst Business Media. I was sort of very interested in thinking about my children and what kind of world they're going to inhabit. And one of my concerns is that it's going to be too easy for them to kind of sit back and have everything kind of spoon-fed to them. And I wondered if you had any experience of seeing how this might apply to education, making the way that people develop and the way our brains develop perhaps result in people who are more like you, rather than someone who's sitting back and watching a lot of Sky TV and drinking a lot of Stella.
It's an interesting question, because one of the problems you have with this kind of information model, and we're going to get into sort of deep, meaningful things here, but we've developed a culture, especially in the US, where we tell our young people that their view matters and they must express themselves, and then as a society we break that bond with them, because they grow up and actually no one is interested in what they're saying, and they didn't make it to be a finalist in X Factor. These are real issues, and so what you've got is a situation where one of the things the internet has done is produced an amazing safety valve for that, which are the blogs no one reads. So, people who religiously write these blogs, and actually no one actually reads them, but they are expressing themselves, and that's great and that's wonderful, and obviously they can do things with that, but because there's this expression without analysis, we're getting into this very dangerous situation where everybody's opinion counts the same. And I think it's a fundamental issue, and I think it's a fundamental issue for engineers to talk about. Because the thing about engineering is, actually, if you get it wrong, the bridge falls down, or the plane crashes. And so everyone doesn't have equal knowledge of things, and we do need to encourage people back to learning fundamentals. Now, the danger in saying something like that and sounding a bit like a sort of Victorian prophesying doom, of course, is that how you get to knowledge may be very different. So, for example, my father, when he went to school, had to learn his times tables in great detail and his spelling in great detail. Frankly, in a world of calculators and spell checkers, that may not be what you should be spending the time on. And I'm sure in this room there are people horrified at that sentence. But perhaps that's the point. Perhaps the next generation is in a different situation. So what you've got is the ability to get to information is completely different. So I look at my 7-year-old, she's just done a project on the Victorians, and she's completely computer literate and just goes on the internet and finds out all about Victorians and gets pictures of them, prints them out, and then sticks them on paper and all sorts of things. That's an incredible resource. But I also want to make sure that when it comes to her being 17, she can actually solve a partial differential equation, because that actually matters. So it does. So there is this sort of dilemma going on about this sort of interplay of knowledge. Yes, all of these things are incredibly good at democratizing access to knowledge, in-depth knowledge. But so for example, if you go, just before I did the talk today, I just went on to Wikipedia to just check the Monty Hall paradox, which is what the doors are called. And there's a dispute raging on Wikipedia about the right answer. And it's a mathematics problem. There is a right answer, it's obvious. But the opinions have become, on Wikipedia, the opinions are just as valid as the right answer. Now, you've got this whole wisdom of the crowds, or is it wisdom of the clowns? We don't know. But, it may or may not work as a model. But I'll tell you one thing. If I want to fly on an aeroplane, I want one that was designed by someone who learnt their engineering and can solve a partial differential equation. I do not want to fly on an aeroplane that was designed by a crowd.
Philip.
Philip British from the Academy staff. Mike, if I could pick up on Lord Brose's theme, but track forward to today. You're now a large company and incredibly successful. How do you keep yourselves ahead of the competition? How do you keep ahead of the Microsofts and the Googles? And perhaps more to the point, what do you do about the next pair of PhD students who are coming along, waiting to take the next bit of business away from you?
We fund them. Yeah, absolutely. The whole model is, we would hope to be in a very good position to be able to understand those people and fund them and give them, so for example, we spun off a business called Blinks, which is it's now about a $400 million business, and it's a video search engine, and that was exactly that situation. We had an incredibly bright young chap, and we said, don't go off and do that, we'll fund you. We gave him the money and we got started, and that's it. So the important point is being open to that talent. And the important thing about the UK especially is we have phenomenal talent here. The output of the top scientific universities in the UK is second to none. Everyone talks about Stanford and MIT, but Imperial and Cambridge are just as good what's coming out. But actually here it's easier to work with those people. And what you should be doing is looking at this incredible resource and backing it. And if that means that they come and work at Autonomy, learn a bit about the other things they need to know, marketing, and then they turn up in my office and say, Mike, I'm off to found my own company, and I say, great, I'll fund it. That's fine. That's exactly the way we look at it.
Last question.
Ricardo Souza, Enterprise Limited. Just going back to the same topic of commercialization, I think you alluded at some point to the use of business angels. So maybe if you wouldn't mind, could you share with us a little bit of the history of how you actually financed your company? Because I think that's probably one of the key challenges for anyone starting a company.
Well, when we started, there was very little venture capital in the UK. And so, not really knowing what we were doing, the first place we went to was the bank, and because that's where the money is. And we went and we met a very nice bank manager in Cambridge, and we explained to him that we had this novel method based on singular value decomposition in sparse spaces. And he listened very politely, and then at the end refused to give us any money, and explained that he normally did loans for people that are setting up news agents. And he gave me one very important piece of advice, which is that people generally stop on the way to work to buy sweets and papers. Now, I've worked very hard since then, and Autonomy now has $1 billion of cash. So what you may well read in the FT in the next few weeks is that Autonomy has swooped on all the country's newsagents, and we will actually be putting into place this master plan. So that didn't work out. And we went to what was then the DTI, and the DTI had a program which was called Innovation. It had a whoosh, some of you may remember. There was a whole sort of ad campaign. And I met a very nice chap who was in his 60s, and as he was pouring me tea in a lovely china cup, he explained to me that he was only doing innovation because he was retiring next year. So that one didn't work. And then, as I say, I was very lucky to hang around in a bar and get a loan of £2,000. So the moral to this story is all good entrepreneurs should spend a lot of time down the pub, and then they'll get finance. The real answer to the question is that £2,000, because we went for these high-value problems, was enough to get the business going. And actually, we didn't actually take in any financing. The business was already doing 4 million of turnover with 2 million of profit by the time we took in the first set of financing. So it was a real bootstrap job, which was actually a great thing because that's how you learn to run a business, because you had to very, very quickly. One of the failure modes you see in Silicon Valley is these companies that start up and they get $200 million, they almost invariably fail. Because the bad thing about having $200 million is you lose focus. And if you lose focus, you lose time. And time is the one thing you can't ever get back in technology.
Well, I'm sure you'll all agree that we've had an absolutely fascinating evening. We've had philosophy of what is meant by meaning. We've had, I'm sure most of you will wake up in the middle of the night worrying about doors and Ferraris. And we have to thank the man in the Soho pub for the £2,000 loan. So I hope you will join me in thanking Mike for a most enjoyable and fascinating lecture. Thank you, Mike.